Hello, class. Okay, so, yeah, sorry about today. To start with, I had to start a little bit late. I had an appointment in the morning and supposed to finish at 8:50, but then I had to drive home. So I was going to be a little late. I said 9:30 just to be safe. And then after about 15 minutes, the internet went out again. So I think what I'll do is just kind of start from the beginning. We were working on a problem when the internet cut out. So I will kind of start this problem over. I'll leave this up, but start the problem over. And just finish the review as a recording and post it online. I think I'm going to have to do something about... I switched internet providers recently, and this one is not as reliable. So might get a hotspot or something to avoid this in the future. But yeah, sorry about that. Okay, so today what we're doing is we're reviewing combination lenses and angular magnification. And so I'm just going to go over the suggested problems for these two topics. And for Friday, we are going to get into the last chapter, chapter 27, where we're going to, we've been treating light as, you picture like a laser beam, just like rays of light that move in straight lines. And then when they hit things, they bounce off, obeying that law of reflection. Or when they change from one medium to another, they bend. They can change the angle and the speed. But light is actually not quite so simple. We know light is an electromagnetic wave. And so we're going to get in, that has consequences. That there are certain things that are properties of waves that cannot be explained by what we've been doing so far. So we're going to start treating light as an actual wave in the next chapter. And we're going to look at the double slit experiment and diffraction. Kind of two examples of the same thing, but the double slit experiment was historically extremely important. It was done in the 1800s, actually, by a guy named Thomas Young. So that's kind of its own topic. And then we will get into just diffraction in general, where basically instead of the double slit experiment, you have a barrier with two narrow slits for light to pass through. Diffraction is just, basically you have a lot of narrow slits for the light to pass through. But break it up into two topics. Now, also on Friday, Chapter 25 homework is due, and Lab 6, which is on mirrors. And we only have one more week of regular class after this week, which will mostly, it'll just be a review. So we have a full week of review, and then the final exam. So if you need more time for Lab 6, we can be a little flexible on that. But I don't want to be too flexible at this point because we are nearing the end. So Chapter 25 homework due Friday. But yeah, let me know if you want to move the lab around a little bit. But anyways, let's get back to combination lenses. So that's what we're going to start with reviewing today. And so, what's on the board here is nothing new. We have the thin lens equation, magnification equation, and how the image and object distances relate to the height of the image and the object. And here, our goal, very often, like say for a particular lens, we know where the object is, we want to find the image. And so we can solve this equation for DI. It comes up enough, it's probably worth just writing down. So we have an equation specifically for DI. So this equation is nothing new. We just solve that one for DI. So the problem, doing the suggested problem from the notes, says a converging lens is located 30 centimeters to the left of a diverging lens. So here's our converging lens, here's our diverging lens, 30 centimeters between them. The focal length of the converging lens is 12 centimeters, and for the diverging lens, it's minus 6 centimeters. And then we placed a postage stamp 36 centimeters to the left of the converging lens. And we want to find the final image and describe that. So to start with, what I did is I drew a ray diagram to find the image due to the first lens. And because we have to be very careful with these ray diagrams, that's more critical when you have two lenses. So we're going to create the image due to the first lens, let's call this I1, and use that as the object for the second lens. And so I want to make sure, so I drew the ray diagram and then checked it with the equation. So what I got for DI using the equation is 18 centimeters. And if there's 30 centimeters separating the two lenses, the midpoint's right here. So that's actually very reasonable with what we got with the lens, the ray diagram. So I just wanted to check that before moving on and creating the second image. This could be really important, like if the image was closer to the diverging lens, there's even the possibility that you could draw it and have it on one side of the focal length where it's actually on the other side. And so that would be a huge problem if something like that happened. So I'll do this kind of one step at a time. So we found this first image, and then I drew the ray diagram to get the second image, and then the internet went out. So what I did, we have ray 1 parallel to the principal axis, and then it's a diverging lens, so it's going to move away from that focal point to the left. And it's kind of hard to see, but this one we go towards the focal point on the right, but when we hit the lens, it'll come out parallel to the principal axis. And so these two rays are diverging, so we trace them both backwards. And we get an image here, which I'm going to estimate for DI2. Based on the diagram, I'm going to make an estimate of minus 4 centimeters. The focal length is 6. We're more than halfway, but so it looks like around minus 4. And minus because it's a virtual image to the left of the lens. So always take the sign convention into account. So this is where we left off before the internet died. So let's plug it in now and check. Now this we have to be very careful. DO is the distance from the object to the lens. Now, so we have to find this distance from here to here. So we know this distance is 18 centimeters. So this image is 18 centimeters to the right of that lens. And so we're 18 centimeters from this one. So this has to be 12 centimeters because the total distance between them is 30. A common mistake would be, we're treating this as the object now. DI for that was 18 centimeters. So that'll be DO for the next lens. No, not that simple. We have to, this is where drawing a diagram is exceptionally useful. So we get this object distance right. So this image is 12 centimeters to the left of the diverging lens, which means that it is positive 12 centimeters. So, plugging in the numbers, we have 12 centimeters. Now this focal length is minus 6 centimeters. And now for the bottom, we have DO minus F. So we have 12, and then minus negative 6, So that would be 18 centimeters on the bottom, in the denominator. And 6 over 18 is 1/3, 12 over 3 is 4. So yeah, getting exactly what I guessed from the ray diagram. Numbers worked out nicely, it was set up that way. So the final image is 4 centimeters, it's a virtual image, 4 centimeters to the left of the converging lens. Okay, now that was part A. Find the final image and find the overall magnification. So I'm going to write down another equation here. So again, let's just solve this equation for HI. So let's find, this is HO, the height of the object. So HI1, the height of the first image, we have minus HO, which we're not told what that is, just fine, and then times DI. So DI was positive 18 centimeters divided by DO, which was 36 centimeters. So we have minus 1/2 HO. And that matches up fairly well with the picture. Half of this height is maybe here. Looks good. Also, the negative sign, it's inverted relative to the initial object. So now we want to apply this. This is now the object for the second lens. So let's find HI2. I2, it's very hard to see the picture. It's so small. But we have a small arrow, pointing down. And so, yeah, let's find HI2. It's hard to even make a prediction, either a half or a third of the original. But let's give that a go. So HI2, that'd be minus HO. So height of the object. So the object is image 1. So this would be plus 1/2 HO. So HO is like the original object. So we have this minus sign in front, but we also have a negative because it was flipped. So it's positive. Oh, and then we have times DI, the distance to the image. That would be, what was that? Minus 4 centimeters. Times DO, which is 12 centimeters. So 4 over 12 is 1/3. So we have minus 1/6. So the height of the final image is minus 1/6 the height of the original image. So if this was like 1 inch, this would be, minus means it's inverted, which it should be. And 1/6 the size. It looks, I said either a half or a third of this. So it's a third. 1/3 of 1/2 of the original HO. Okay. So we have a much smaller image here. And inverted with respect to the original. Is it real or virtual? It is virtual. And it's inverted and smaller. So lots of parts to that question. So that's it for combination lenses. Okay, so let's talk briefly about angular magnification. So an example of a combination lens would be like a telescope or a microscope, where you're going to be looking at things that are extremely small, or at least appear to be very small. You could be looking at in a microscope like a cell or something, which is typically very small. In astronomy, you could be looking at a planet, which is large, but because it's so far away, it appears small. So we define angular magnification by like the angle, like say you're the observer here, here's the object. So like the angle subtended by the object. Okay, and for angular magnification, we've got a picture here. I'm going to write this down. It's a bit of an approximation, but it's the height of the object divided by the distance to the object. And so we can examine magnification for different objects. Let's just go through the two suggested problems, though. So to start with, here we have a quarter with a diameter of 2.4 centimeters. So here, let's say this is the quarter. So I didn't even define magnification yet. Theta is the angle subtended by the object. And basically, remember that equation, S equals R theta? As long as theta is in radians, that's basically what we're looking at here. This would be the dO. That would be, S would be like the height of the object. So just based on this equation, height of the object would be dO times theta. So theta is HO over dO. Now the magnification, we say theta prime is the angle that would be subtended after looking through an object, through a lens or a combination of lenses. So if we use a lens or something and make the angle twice as big, then that would be magnification of 2. And in the notes, there are various examples like telescopes and microscopes. But yeah, let's just look at the two suggested problems. So here we have a quarter is held at arm's length. Oh yeah, the reason there's an approximately equal to is because, the arc length would be curved a little bit, where we just have a straight line here. Pretty insignificant though. So we want to find the angular size of the quarter. So remember, we have 2.4 centimeters. That'd be 70 centimeters times theta. I'm going to call this Q. Theta for a quarter. So that'd be 2.4 over 70. It's a pure number, no units. So I'm getting 0.03 for radians. You don't have to write radians, because if you don't write anything, that's implied. So this is a quarter. Now, let's look at the sun. The sun has a diameter. So here we are on Earth, we're the observer. The sun has a diameter of 1.39 times 10 to the 9th meters. And the distance to the sun is 1.5 times 10 to the 11th meters. So what is the angular size of the sun? So again, just using that like S equals R theta, or theta for the sun, that'd be 1.39 times 10 to the 9th meters. And I'm going to write this as 150 times 10 to the 9th meters. So those cancel. So 1.39 divided by 150, this is 0.0093 radians. So basically, a quarter at arm's length is actually significantly greater in size than the sun, or parent size. It might seem surprising. The sun looks a lot bigger. I think it's because of the atmosphere. It kind of just lights up an area of the atmosphere, making it look bigger than it actually is. Okay, got one more problem. I'm going to pause for a moment, and I think I'll just do that on a second recording. So I'll be right back.